Okay, so we're recording. All right, thank you so much, Sloan. It's been a great privilege to work with you over the past several years. I've learned so much from you, and definitely look forward to continue to work with you in the future. I know we'll keep in touch and collaborate going forward. Before I start, I actually wanted to talk about the title of my dissertation. And so I was heavily influenced by Greg's use of haikus for summarizing his research. I think they're a very elegant way to convey the main point of your findings or a subject matter. And so I came up with this haiku, seas in hot water, marine heat waves on the move and following the heat. And so you'll learn a little bit more about why that was chosen as I go through this talk. So you can't really talk about marine heat waves without addressing head on that there is this massive warming trend in global sea surface temperature. So this is the monthly sea surface temperature anomaly averaged across the entire ocean. And you can just see this rapid warming trend over the past 40 years. But not only is there's this warming trend, but there's considerable year-to-year variability. And so you have internal variability acting on top of a warming climate that's primarily due to anthropogenic influence. Now, this warming trend is not spatially uniform across the globe. It varies. Some places are warming faster than others. So here is that trend now computed for each location in the ocean. And this is computed over about a 40-year time series where red is warming faster and blue is actually cooling. And so this data that I'm using is actually a blend of both satellites and in situ globally. And this is the type of data that I'll be using throughout the rest of the talk. The talk is on marine heat waves. So let's first consider a case where we don't have this pervasive warming trend. So this is a synthetic time series of the sea surface temperature. And there's no trend here, so it's just there's a mean and there's variability about that mean. So where the time series is kind of yellow or orange, that's when the temperature was above average. Where it is cool, whereas blue, it is below average. And so in this stationary climate where you don't have a trend, you have equal chances of getting an extreme warm event or an extreme cold event. And this range of variability is something that species have adapted to over time, and they're able to cope when there is an extreme event. Here we're defining extremes when the sea surface temperature anomaly exceeds some threshold that we define, usually over a 30-year period. So in a stationary climate, species can cope, meaning that they can, if they're migratory, they can move to where there's more favorable conditions, or if they're sessile, like seagrass, they can slow their growth and put that energy into survival. Now, what happens when we have a warming trend? So we'll extend this time series out into the future. And now you not only have this great variability, but it's happening on a in a much warmer world. And so your really warm extremes become more intense, more frequent, and longer lasting, as you can see here. And your colder extremes become less common. They're less severe. And this is if you just shift the mean to a warmer end and don't change the variability. So what does this mean for the ecosystems? Well, they're seeing temperatures they've never experienced before. So these unprecedented events occur more frequently. And as the temperatures rise, these heat extremes become more deadly. And this is when we as people start to pick up on these changes and we start to, I think, care a little more. When you see a starving sea lion on the beach or, massive die-offs of fish, coral bleaching, or the fact that whales have to change their migration patterns and get caught up in fishing nets. So these are kind of the visceral responses to a warming ocean. And my research is focusing on characterizing those extreme events. So we call these marine heat waves. The analogy to us on land are atmospheric heat wave events where the temperatures are really warm and humid for a period of time. We suffer as humans. Well, species in the ocean also suffer when that temperature rises. There's been there's been definitions proposed for quantifying a marine heat wave, but I think simply quantitatively, you can call it a discrete, prolonged, or and anomalously warm water event. And this is just again, this is a synthetic time series, but it conveys shows you what a marine heat wave looks like and how they're defined. If we actually take real data and apply this definition over the entire globe, we can then begin to characterize certain events that have occurred. And so marine heat waves occur worldwide, and this is a composite map. So it's multiple marine heat wave events put on the same map. And next to the warming area are the dates that marine heat wave occurred. And so this is the temperature anomaly. Here, this paper is using the 99th percentile. So it's the temperature anomaly above when it exceeds the 99th percentile that it's showing. And so probably what catches your eye is this massive warm pool of water in the Pacific during 2015, 2016, or 2016 here. And that was named the blob. And so a lot of people in the in North America recognize this event for its impacts locally. But people in Australia might be more familiar with the marine heat wave that occurred during February 2011, also referred to as the Ningaloo Nino. And so these marine heat waves, they don't look alike. They actually can evolve quite differently, have different spatial patterns, intensities, and durations. And so really the essence of this dissertation is getting at what are those patterns and how do marine heat waves evolve. Okay, so there's a central theme of my dissertation, and then there's 3 core chapters. The dissertation seeks to understand the spatial temporal evolution and persistence of marine heat waves. The first chapter, as Luann mentioned, I'm not going to talk about today because that's already been presented to the department. This chapter was published in the Journal of Geophysical Research Oceans in 2018 with Michael McFadden. And so it looks at the drivers of the seasonal mixed layer heat budget and trying to understand the sources of model biases based on that seasonal cycle. Today, what I'm going to focus on is chapters 2 and 3. So chapter 2 looks at the subsurface evolution of recent Northeast Pacific marine heat waves. And then chapter 3 proposes a new way to characterize the 3D connectivity of marine heat waves, so in both time and space. So some of the guiding questions and grand challenges in chapter 2, the subsurface ocean often gets overlooked as a potential contributor to marine heat waves, and that's mostly because we don't have reliable observations, or they don't go back far enough in time that we can compute a climatology from them. Using Argo, we're going to ask what the evolution of subsurface anomalies were during recent Northeast Pacific marine heat waves, where we have really good both spatial and temporal coverage of subsurface temperature and salinity. In the last part of my talk, we're going to explore the complex spatial connectivity and temporal behavior of marine heat waves globally. And the question we really wanted to get at was whether local analyses like heat budgets really tell the whole story of how marine heat waves behave and evolve. Okay, so let's dive into the second chapter here. So this is a paper that is currently in review, and I want to acknowledge my co-authors on this. So Greg Johnson, Luann Thompson, John Lyman, and Steve Reiser were very much a part of this study and very helpful. There's 3 motivating questions. So the first is, how did the subsurface evolutions of 2 recent marine heat waves differ in the Northeast Pacific? So we'll be talking about an event that occurred in 2013 and persisted through 2016. And then we'll talk about a more recent event and ongoing from 2019 through 2020. And we're going to look at the subsurface evolution and characterize what changes in water mass properties occurred. And then we want to understand what role does the subsurface play in this long-term memory and persistence of marine heat waves. Just to orient you, these are the 2 events that I'm going to be talking about. So this is the sea surface temperature anomaly on a given month. So on the left is January 2014, on the right is November 2019. And I picked these dates because that's when the sea surface temperature anomaly was the strongest in the same location between these 2 events. So I looked for where they looked similar. So the red is indicating above average sea surface temperature anomalies, and blue is colder. The diagonal lines here are indicating where the sea surface temperature exceeded the 90th percentile. And so we consider that a marine heat wave. So you can see that the marine heat waves covered a pretty much similar area between both of these events. Okay, so let's talk a little bit about the drivers of these events just to get oriented a little more. So the 2013 to 2016 marine heat wave really got its start earlier in 2013 when there was an unusually high pressure system that parked itself over the Northeast Pacific. It was nicknamed the Ridiculously Resilient Ridge, and it had remote influence from the Western Tropical Pacific. There was warm SSTs there, abnormally warm, and that changed the convection scheme in the tropics and propagated a planetary scale wave called an atmospheric Razi wave to the mid-latitudes that disrupted the normal circulation over the North Pacific. And so if you think about going outside on a really nice day, there's high pressure, clear skies, and light wind, well, it's exactly kind of the conditions that the ocean was experiencing in this location. So that lack of wind reduced the evaporative cooling over the ocean. And so essentially the ocean wasn't able to cool like it usually does in a typical winter. So what happened because of that, it warmed the sea surface temperature, as you can see in the map in the top right. So there's warming right centrally located to where that high pressure system was. And those winds prevented cooler water ejecting from the north and reduced the vertical entrainment of cold water below the mixed layer. So these were all the right conditions to really warm the sea surface locally in this region. But the anomalies didn't stay in one place, they moved around. So shortly after it started, it propagated to the coast in fall of 2014. And it lingered there through the winter of 2014, 2015, and into 2016. And what studies have found was that there was an effective component to this migration, but also that those anomalies were locally reinforced. So what happened last summer was quite eerie of what fears of that we were heading into another marine heat wave that we saw starting in 2013. And a lot of the media was abuzz with concerns that we might have mass die-offs of marine life again, or that this warming would then disrupt our weather. And there was a really nice study done by Dylan Amaya and his co-authors to look at the local drivers of this marine heat wave. And the main difference between 2019 and 2013 was the season that these marine heat waves evolved, essentially. So 2019 was summer intensified. It was actually caused partly by a weakening of the North Pacific subtropical high. That weakening actually reduced the wind speeds, and so you had a reduction in evaporative cooling and also a thinning of the mixed layers. So the ocean was more readily able to accept warmth from the atmosphere. And Dylan also found that that SST anomaly was reinforced by a positive low cloud sea surface temperature feedback. So what that means is when you warm SSTs, you warm the atmosphere, that makes it more stable, and you have fewer clouds, so more shortwave radiation is able to reach the sea surface and warm it. So as oceanographers, we wanted to look at what the subsurface evolution was during these two recent events and compare them to see if one was more unusual than the other, or if they were completely different events. So here are those same sea surface temperature maps that I showed earlier. Now I'm taking the monthly time series of anomalies averaged in that box that I've drawn in the top, and I'm displaying it in the middle panel. So we have 2004 to 2020, and I'm drawing lines to where those snapshots are taken. And you can see that those had the maximum temperature anomaly since 2004. The red markers are showing other months that were considered a marine heat wave. So it gives you an idea of the persistence of this event in this location. But we also have subsurface data, really good subsurface data. So we can take a peek at the upper ocean to see how deep these anomalies persisted and how intense they were. And so during both of these events, you can see clearly that there was warming down to 50 meters at least, and that warming extended deeper in 2014 and hung around for a very long time, even after the surface cooled. So let's talk a little bit about the data that I'm going to be using for the rest of this part of the talk. I'm using observations from the Argo array. So this is an autonomous profiling float. This program started in 1999 and now has over 38,000 active floats and more than 2 million hydrographic profiles. So that's amazing. So just to show you what one looks like, this is me holding an Argo float back in 2015 off the stern of the RV Thomas G. Thompson. So these are the kind of vessels oceanographers take out to sea to deploy these floats, and it's going on right now as we speak. This array is actively being replenished. And if you take a look here at the map, I'm drawing your attention to the Northeast Pacific, where we have a really good spatial and temporal coverage with Argo. So over 100 profiles in a 1 degree box. So that's pretty good. So using those profiles, we're using a climatology called the Rimmick and Gilson Argo climatology. So they take those profiles and they objectively map them to a 1 degree longitude by 1 degree latitude grid, and on 58 pressure levels from 2.5 to almost 2,000 decibars. And so from this product, we have monthly mean temperature and salinity from 2004, when Argo first approached sparse global coverage, through June 2020. After we have those fields, we further smooth them with a 5-month Hanning filter and a 6 degree lowest filter to reduce any leftover mesoscale noise. So we're gonna pick a location in the Northeast Pacific that kind of represents both the marine heat waves that I mentioned before. And from Argo, we have temperature and salinity down to about 2,000 decibars, but we're just gonna be looking at the upper 200. And with temperature and salinity, we can then compute the potential density. So this map in the top right corner is showing you the location that I'm grabbing from that Rimmick and Gilson Argo climatology that has these map fields. So what you can see at first is there's a very pronounced seasonal cycle in the upper 50 decibars or so. Decibar is approximately equal to a meter. And so if you're not an oceanographer, you can think as pressure like depth. So it's going from low pressure near the surface to higher pressure with depth. So there's a seasonal cycle. In the summer, you can see it's warmer, fresher, and less dense. In the winter, it transitions to being more cool, saltier, and more dense. But we want to know what the variability was like during these marine heat waves. And you can see that from these plots, but it's kind of hard to really draw that out quite yet. So what we want to do is we construct the mean and the seasonal cycle across this entire time series. And then we remove that out from the data. So we're just left with the anomalies that have the trend in them. And so this is what it looks like. So this is the sea surface temperature anomaly on the top plot and the salinity anomaly on the bottom plot. And I've also contoured absolute density, so lines of constant density or isopycnals. And so during the 2014 marine heat wave, we see that it was much warmer, but there was also a really big salt anomaly in the lower panel. In 2019, it was also warmer near the surface, but there was a really big freshwater anomaly, that's a fresh salinity anomaly. And that fresh anomaly actually caused the surface waters to become lighter. And that's really clearly seen by the depression of this isopycnal, where it usually outcrops in winter, but here it's depressed. And so this fresh anomaly during actually 2018 through 2020 lowers that near surface density and it makes it more buoyant. So what caused this freshwater anomaly? Well, first we thought to go look at the precipitation anomalies. And here we've taken the 2018 anomaly of precipitation minus evaporation. And so where it's green in the top plot, it means that there was moisture added to the sea surface. And where it's purple, it was evaporated away. Furthermore, we can look at the 2019 precipitation field minus 2018 to get the tendency anomaly, where green means it was wetter in 2019 and purple means it was drier. So there is a a freshwater precipitation anomaly seen in these maps that could be contributing to the reduction in salinity shown here. So these are the same maps as before, but now I'm showing you what the density anomaly was, and we can see that it was much lighter in 2018 through 2020. So we want to understand what effect this has on the stratification. And so just as an example, I'm going to pull two density profiles during the dates that had the peak warming in both marine heat waves. And so you can see density is lighter on top, it gets heavier as you go down. 2014 was, this profile is chosen during the winter when the mixed layers are deeper, so there's not much change in density until you hit about 50 decibars, whereas in November, the mixed layer is normally a little more shallow, and so you can see that that change doesn't occur until 25. So if we look at the change in density across this layer, we can compute a metric here, quantity here, called the bulk stratification. And so it's really essentially the density difference across this layer. And when this density difference is greater, that means there's more stratification. The water is more stable. When that density difference is smaller, there's less stratification. It's less stable. So this is just an example of one time, but we're going to do this across the entire time series to see how unusual this bulk stratification was. And we're going to be looking at the anomalies so we can compare different months. Okay, so here is the bulk stratification anomaly from 2004 through 2020. When it's positive, that means, remember, it's increased stability, it's more buoyant. And in both 2014 and 2019, it was really anomalously high, so it was really stable, but 2019 blew all the other months out of the water. So because of that freshwater anomaly that I showed earlier, it really increased the stability of the water column. And this does two things. It first reduces the amount of cool water that can be entrained into the mixed layer. And it also keeps the warm anomalies closer to the sea surface when it's stratified. And that actually helps that water warm because it's a smaller volume of water that the atmosphere has to warm. So the maps over here are showing kind of the spatial distribution, if you will, of the snapshots in January 2014 and November 2019. So you can see that there was increased buoyancy essentially in both of those boxes, increased stratification, but that increased stratification was much more widespread in 2019. So it's likely hypothesized that the increase in stratification in 2019 prevented the warm anomalies near the sea surface from mixing as deeply as the 2014 event. And so we're going to look at that next by here again looking at the subsurface temperature anomaly. So this time we're averaging the subsurface temperature in this box up here. And then we're grabbing over 19,000 Argo floats from 2004 to 2020, and we're going to compute the mixed layer depth with a density difference. And again, I've marked those 2 months, the peak of each event. And so you can see the mixed layer depth was really shallow during the winter of 2014 and 2015. And the anomalies in 2014 and 15 penetrated much deeper than they did in 2019. So one way to kind of get at the memory that the subsurface plays is to compute the ocean heat content. And so I'm going to compute it over 3 equal thick layers of the ocean. One will be near the surface in the seasonal varying mixed layer. The second one will be in the pycnocline area, so that's the middle. And then the deep layer is kind of representative of the interior. So what you can see is that there was really strong heat content anomalies during both of these events in the near surface, where you have most variability in temperature. And then as we quantify the heat content anomalies in the middle and deep layer, it reveals that there is a persistence in that heat content with depth, and that it lags the surface considerably as you go deeper. And so this kind of suggests that the subsurface is able to remember the surface expression of marine heat waves. So in a warming world, we expect that stratification will become stronger. And so this suggests that as stratification increases, this mechanism of storing anomalies deeper into the ocean won't be as effective. And so that could make the surface marine heat waves worse. Okay, so I would like to summarize this chapter with 3 haikus and 2 videos. So the videos are showing the sea surface the temperature anomaly and salinity anomaly at 2.5 decibars during the 2019 to 2020 event. And I will read the haikus. So return of the blob with warming and freshening, hence more buoyancy. Summertime heat waves increase stratification, inhibit mixing. Wintertime mixing, warming penetrates the deep, provides memory. So the takeaway from the 2019 event was this freshwater anomaly really set this marine heat wave apart and kept those anomalies near the surface. Okay, so moving into the last chapter, this was a project I started with Luann Thompson and Dan Witt and David John Gagne at NCAR. And it's been really fun to work on. This is the same image I showed earlier with those composite of different marine heat waves. So this chapter is really getting at how do these large scale and persistent marine heat waves evolve. We also wanted to ask if there's tropical linkages between remote marine heat waves. We know the tropics are a really important driver for marine heat waves, and there's likely a connection there. So we're going to look at that and then also characterize some prominent 21st century marine heat waves to see how unusual they were. Just to start, so traditionally what folks have done, they've looked at local metrics of marine heat waves. And it's not surprising that some of those look very similar to the standard deviation of sea surface temperature anomalies. So the standard deviation is showing you how variable the sea surface temperature is in a particular location. And so in the western boundary currents in the eastern equatorial Pacific, you have really variable temperatures. When you compute the marine heat wave intensity, you see that the most intense marine heat waves also fall in the regions where you have high standard deviations. And here we're computing a marine heat wave where SST exceeds the 90th percentile locally for at least 5 days with respect to the 1982 to 2016 climatology. So we can also do this for duration, and we find that the longest duration marine heat waves occur in the eastern tropical Pacific, and that's undoubtedly related to El Nino events in this region that have a 3 to 7 year periodicity. So what are we going to do? So we want to track marine heat waves in space and time. So we're proposing a new algorithm called Oceanography, and it can be used more generally for tracking other oceanographic extremes. So the data set that I want to walk through as an example is the satellite and blended in situ observations of sea surface temperature, or the optimum interpolation sea surface temperature data set. We're going to be using monthly means from September 1981 through present. And these are mapped onto a 1/4 degree resolution grid. The first step that we're going to take in Oceanography is to pre-process our data. So this is to find the temperature anomalies. So to do that, we're going to start here at just one time series. So we have sea surface temperature on the left. From that sea surface temperature, we can compute the mean, the trend, and the seasonal cycle. And we do that over a fixed 30-year period. Once we have those components, we then subtract it from the sea surface temperature to get our detrended sea surface temperature anomalies on the right in the blue. So we do that every single time point. So we can have maps here to show the subtraction. On the left is the total sea surface temperature field. You can see it's really detailed, and there you can see eddies in there. The middle is the more smooth mean, trend, and seasonal cycle. Once we remove that trend from the total map, you get what's left over, and that's the anomalies. And so these maps are taken just at a snapshot in January 2014. Okay, so after we do that process, we now have a map of sea surface temperature anomalies. And we would like to know which of those anomalies are a marine heat wave. And so we take the 90th percentile and we find where SST exceeds the 90th percentile. In those locations, we keep the SST anomaly. So you can see now that those background SSTs start to dissolve away and we're just left with those marine heat wave anomalies. The next part of Oceanography is the anomaly detection. So once we have those marine heat wave anomalies, we want to find the outlines of these events so that we can track them. So we're gonna walk through an example here in the Northeast Pacific. So this is January 2014 again. And once we have this image, we pass it through a series of morphological operations. So the first one is called closing. And so this is a dilation of your image followed by an erosion. So now we have a binary image where the red color means there's a marine heat wave. The white color means there's no marine heat wave. Dilation essentially adds a layer of marine heat wave points around your original object. And the purpose of dilating is to fill holes in the objects and to smooth the outside edges. After dilating, we then erode that boundary away, and that gets rid of any small isolated features while still retaining the shape of the object. So after closing, we follow it by an opening. An opening is erosion of your image followed by dilation. And so we go through that same process until we get this final image shown in the bottom left. And those dots are showing where we had the original marine heat wave candidate points from the anomaly detection up here. So now we've gone from this kind of pixelated image of what our marine heat wave points are to now these closed objects that we can then define a shape or an area to them and better characterize them. So once we go through this, we have, a whole data set of all these objects. And some of them are too small, and we don't really want to look at those. We want to characterize the really big and impressive marine heat waves. So we take all of those objects and we form this distribution of their area. And so we choose a size threshold. Here I'm choosing the 75th percentile. It seems like a really high threshold, but you're actually keeping the majority of your data shown by those orange bars. And what we're throwing away are what we call heat islands. That would also include eddies in this case. So we've eliminated the really small objects and we're left with the ones that we want to characterize. So that turns out to be, over this 40-year time series, this data set, we have over 5,800 marine heat wave objects detected. So just to recap where we've gone, we've started with sea surface temperature. So this is showing January 2014. From that data set, we were able to extract out the marine heat wave objects that we're going to track next. And those are shown by the different colors in the right spinning globe on the same date. So the only thing that's really left to do now is to connect these objects in time and space. And so we use a connectivity element that considers a marine heat wave as the same event if they share an edge or if they overlap in time. The unique thing about Oceanography is that it allows marine heat waves to split and merge back together. And this is possible because we run Oceanography both forward and backwards. And so it's able to remember what objects belong to the event from where they touched in the past. So this is a really unique way of following the same marine heat wave around the globe. After doing this, we now have over 1,100 marine heat wave events worldwide. And a single marine heat wave event can be comprised of multiple objects. So let's just go through an example here. I'm showing you the marine heat wave in the Gulf of Maine in 2012. Fun fact, this is when I actually got started in marine heat wave research, was during this event. I was living in Maine at the time. So this event was pretty regional. It only really stayed around in the Northwest Atlantic for 8 months. It was atmospherically driven. The red is showing you where the marine heat wave was. The white is just the background, and we're just isolating this event to show you its progression in time. If you look at the map in the top right, this is kind of an imprint of that marine heat wave's intensity over the duration of the event. So we call this the cumulative intensity. And you can see that the most intense severity of this event was in the Gulf of Maine, the Gulf of St. Lawrence, and part of the Labrador Sea. So this is a fairly typical marine heat wave that we would characterize with Oceanography. The next example I want to draw your attention to is the actual global evolution of what we think of as the blob. So to characterize the blob, I went back into Oceanography and found where there were anomalies in the Northeast Pacific that corresponded to the timing of anomalies that we knew from other studies. Finding that event, I was actually able to trace back the origins of that warming to the tropical Pacific. And Oceanography connected these marine heat waves in time and followed them. So it really reveals this global marine heat wave as it moves and connects in time. This is a super unusual event. It lasted 53 months, actually beginning in July 2013 and lasting through November 2017. You can see the major El Nino in 2015 and 16 developed that influenced this, and it eventually dissipated into the Atlantic. Looking at the heat map, you can definitely see that the most severe aspects of this event were in the Northeast Pacific, like we know from other studies, but the point is that Oceanography, but with not telling it really any other information besides how these events connect, are able to trace this all around the globe. So we do this not just for these two events, but for every single marine heat wave that we detect. And then we can come up with a catalog of different marine heat wave metrics. So we look at the intensity, duration, and the area of all these marine heat wave events. So here is the maximum intensity. You can see the maximum intensity really clusters around 3 degrees with a fatter tail as you go out to the more extremes. At the bottom is the time series with each event's maximum intensity plotted on it. And the blob, what we're calling the blob, and the Gulf of Maine marine heat waves that I just showed are also plotted on here to compare how unusual they were. You can see the blob was way out there in the tail. It was a very intense marine heat wave where the Gulf of Maine was closer to average for this. So a lot of the marine heat waves congregate into that 3 degrees C. So the next metric we're going to look at is duration. And duration has more of a heavy tail. Most events last all but 1 or 2 months. The blob is an exception. It lasted for 53. And the Gulf of Maine was actually pretty unusual, being 8 months. You can see that it was not falling within the conglomerate of marine heat waves down at the 1 or 2 month range. So this gives you a sense of how long these marine heat waves are lasting. Okay, and the last metric we have here is the area. So this is the total area. And this one is a little less clear. So it's a fat tail, but there's a lot of variability here. The blob was by far the largest marine heat wave that we tracked. And the Gulf of Maine was also quite large, but there's a lot of spread in the area. And that probably has to do with how connected different marine heat waves are. Okay, so coming to the end of this section, there's 3 more haikus. Global and local Oceanography reveals new pathways linked through the tropics. The blob sets new records for the longest and largest marine heat wave yet. Heat waves split and merge, connected in space and time, a new paradigm. So why should you or I use Oceanography? Well, I think it overcomes the limitations of characterizing the complex and spatial connectivity and temporal behavior of marine heat waves as they evolve. We really didn't have a tool to explore this before. We were just doing boxed heat budgets or grid point-wise analyses. So this really enables us to characterize new spatial patterns like we saw with the blob and behaviors of some of the most dangerous marine heat waves of the 21st century. Most importantly, Oceanography provides a new public data catalog of observed marine heat wave metrics and trajectories. So this is a ripe data set if you want to take in and explore machine learning applications. And it provides also a new set of tools that we can probe other extreme phenomena. So for example, You can look at oxygen extremes and how they move around, harmful algal blooms, or even the movement of heat from El Nino. So it's a really exciting product, and we hope to very soon make it publicly available so that other people can start to play with it. So here's my take on where this field is headed. I honestly think that the subsurface is the new frontier for marine heat waves. This photo right here is showing you a glider track of temperature that was created by Jessica Ben-Thuisen. And we're increasingly getting better resolution of data in the subsurface. And right now, we don't know that much about subsurface marine heat waves and their impacts. And it's clear from the second chapter of my work that the subsurface really matters. Okay, and then I think this connection between the local and remote, marine heat waves through the spatiotemporal evolution and forcing is really important. It's very clear that tropical Pacific variability plays an important role in driving marine heat waves, and that in fact, when you include it in models, it improves your prediction skill, as shown by here in Mike Jaycock's paper. Okay, so I like to conclude here with some acknowledgements. First, I have so much gratitude for my committee. They have been a real soundboard during this PhD and really helped guide the direction of this research. And I really do appreciate their collective expertise. Especially Luann being able to come knock on your door or text you has been really helpful to get your input. This is the reason why I think science is so much fun, is because all of these people, I'm a huge people person and I love interacting with all of you. You're honest, hardworking, and inclusive and creative. And you aspire me to become a better scientist and a collaborator. So thank you. And and I'd like to special thanks to David, John, Dan, and Luann for their immense support past several months with the pandemic and trying to wrap up this tracking work. So it's been a lot of fun, and I'm sure we will continue to work together in the future. This PhD has had a lot of interesting support over the years, and I'm so grateful, particularly to Microsoft and the Leonardo DiCaprio Foundation. They provided an incredible amount of compute resources on Azure, which it's been really nice having my own virtual machine to run these simulations. So thank you very much. Tableau also, they taught me a lot about working in industry and about machine learning during a summer internship, and I'm really thankful for the connections I made there. The advanced study program, although I was only in Boulder for a week and a half before the pandemic, I'm very grateful for the team there and making sure that the work was able to continue remotely. And several other organizations that have helped provide funding for travel or data sets. So thank you. And big fan of open source software, as many of you know. These are just some of the tools that made my job a whole lot easier. Especially Xarray and Scikit Image. Of course, Azure and Sizzle supercomputers I use every single day. But of course, with all of these technologies and these complicated packages, I couldn't have done it without the eScience Institute's help, especially Amanda Tan, who really helped me get over that steep learning curve early on. So thank you. The community in the School of Oceanography is phenomenal. I'm always so impressed by this group of grad students, and I can't wait to follow your careers as you go forward and to stay in touch. Especially like to thank my cohort. It seems like forever ago we were wearing those silly hats during our first Friday debut in 2015, but we've all grown up so much since then and have produced some really great science. So thank you to you all. I have to mention my Seattle friends here. They've really helped me strike that healthy work-life balance and even introduced me to type 2 fun. I wouldn't have imagined that I would be climbing Mount Rainier or biking 100 miles in a day. And I think when I look back on my 20s, these are the memories that I'll look back and say, yeah, I really did that. And lastly, I have to thank my family. They have been my greatest cheerleaders and supporters throughout this process. They've listened to me and my science over the years, and they're just the reason I keep going. So thank you to my sister, Lauren, brother-in-law, Nathan, for being my also my adventure buddies, and then my mom and dad, Melinda and Mark. Thank you. So just to conclude here, I'll leave up the 6 haikus that summarize chapters 2 and 3, and I'd be happy to take any questions.